One of the most game-changing features that was added to Inspire was the ability to do multi-body simulation, MBS, in the Inspire interface. The great thing about doing motion simulation in Inspire is it's all geometry-based. A large portion of it is automated, and it's very, very easy to set up. And it allows you to review the behavior of your kinematic systems, and then ultimately even feed that behavior, those kinematic systems, into an analysis or into an optimization. So what we're going to do in this tutorial is we're going to walk through the process of setting up a motion analysis. And the way that we're going to do that is, of course, from the motion ribbon. And motion is done essentially in a left to right manner along the top row of icons here. Where we're starting with ground and moving on to rigid groups and joints, and we will skip some of these, but we'll talk about them. And it is kind of a process-based approach to creating a motion analysis. The first thing that we're going to do is we're going to talk about setting up ground, and we have to set up a ground because that's what's going to hold on to our part. Our part has to be moving relative to something, and it's really the ground that is what we're moving relative to. And there's a couple of different ways about doing it. In this part right here, you can see we have no ground per se. This, by the way, is a parasolid model of an excavator. It has many, many different parts in here. And we're going to simulate this turning, and we're going to simulate this arm and bucket moving. We're going to do that by the creation of some motors and actuators. But first, like I said, we have to establish a ground scenario. So we could, if we wanted to, we could draw a rectangle and establish that as ground and let it sit on the ground. But in the case of this, we pretty much can just define this chassis here, the suspension, and these tracks as the ground, because if we think about the way that this is going to be situated, it'll be sitting on the ground, and these will be stationary. Now, your establishment of ground is going to highly depend upon what you're looking to analyze, but essentially just think what stands still and establish that as ground. And you, like I said, you can go all the way to actually creating a ground, but then that's going to require some context, defining the connection between the parts and the ground. It gets a bit more complex. And one of the rules of thumb in motion analysis is we want to make things as simple as possible. And we'll talk more about that. So the first thing that I want to do is I want to come here and activate my ground. And then I'm going to pick my base here, and my base here, and my base here. Right click, and if we look in the model browser, you can see that those now have a little ground symbol next to it. And one thing that I like to do, and we'll do this quite frequently through this tutorial, is I'll quickly run it. So let me come here and set the parameters. I'm just going to set it for, say, a second. And we'll animate actually we'll leave it on animate when solving for right now. And then what I like to do is I just quickly run it because it just shows me what I've done and make sure that each step is working the way I anticipated. So if I click Analyze Motion, you'll see it begins to go, and we see the excavator itself begin to slide off, but most importantly, those treads and that suspension, that chassis, that truck, whatever you want to call it, stays in place. But this also has revealed another problem to me, is in this case, gravity is going in the wrong direction. So we'll kind of break from going across, and we'll pop here to gravity. And we'll select that. It looks like we want it in the y-axis, and it defaults to the negative, and that is the standard gravitational acceleration. So now if I quickly run it again, exactly what I was expecting to do. So that takes care of our ground, and it takes care of gravity. So let's move on to the next section here, which is rigid groups. Now, rigid groups combine things together. And it's a way of taking a number of parts and making them act together. And the easiest way for me to describe that is actually to jump a little bit ahead to joints here. And so let me come to joints, and we'll talk more about joints, but let me just establish a quick joint here. And we'll make it hinge. I will explain that. But what I want to show now is after establishing that joint, that's going to connect the cab to the suspension. But you're going to see all of these little windows, which are all separate pieces of geometry, are going to start falling through. And the problem that creates is I could go through and I could Boolean them together and geometrically Boolean them together. I could create contacts between them. I could create joints between them to keep them in place. But all of, like I said earlier, the goal is to make this as simple as possible. And the easiest way to make this as simple as possible is to create a rigid group. And what the rigid group does is it says all of the things that are in the rigid group, even though they're separate pieces of geometry, are going to act together. And that means because the cab here is now through a joint connected to the suspension, and it can't move, it will prevent the rest of these from moving because they'll be following whatever behavior the cab does. So I'm going to come here to rigid groups. I'm going to grab each one of these pieces of geometry and make sure I get them all. We'll rotate around and we'll get this window, this window, this window, and just a quick look around. And it looks like we are pretty good there. You see it, since I selected everything within chassis, and I could have selected it just by grabbing them up here, it renamed it to chassis. I click create, and now it goes faded because something can only belong to one rigid group. But you'll see now if I come here and I run the animation, all the windows and the doors stay put, not because they're connected mathematically to the geometry or to the cab, but because the rigid group causes them to stay put because the cab is staying put. So that's an easy way to connect multiple parts together without using a more advanced and more analytically intensive option. The next tool, as we move left to right across our icon bar here, is joints. And joints is a tool that we're going to use to connect geometry together. And I know it's going to sound kind of like a broken record, and I keep saying this over and over again, but the more simple you can make your model, the happier you're going to be, because the quicker it's going to run, the more stable it's going to be, and the easier it will be to debug in case you run into issues. And joints are the simplest method. Well, I guess rigid groups would technically be the simplest method of connecting geometry together. But joints are the simplest method of connecting geometry together so that they can behave independently but still maintain some connection. And we quickly created a joint right there. But now let's go into what we did. So once I come into joints, and the first time you select joints on your model, it can, depending upon the complexity of your model, it can take some time before you'll see this view, because it's going to go through and it's going to inspect all of the geometry and find things that can be jointed together. In particular, it's looking for geometry that shares faces. It's looking for holes that run through multiple parts. It's looking for cylinders that go into a hole. It's looking for any form of geometry that really can be defined as a joint. And the type of joints that we have, if I come back to here and I click this, you'll see we have a hinge, cylindrical, translational, ball and socket, and unknown. And we're going to focus on these four. What we're going to use in this model are just hinge and cylindrical. There's also a planar joint. We don't have any planar in here. A planar would be a flat surface touching another flat surface. But in this case, a joint allows a specific type of motion and only that type of motion. So the first on the list, and what we defined up here, was a hinge joint. A hinge joint allows rotational motion. So it allows this just kind of show you what's going on here. Let me get right click out of here, and we'll flip this over, and I'll hide that. So you see, what we have is this little cylinder here, and it's going into a hole, a pocket, on the suspension underneath. So the hinge joint will allow that cylinder to rotate within the pocket. And red means it's found it, but it hasn't been defined. Green means that it has been defined, and in this case, it's defined as a hinge. And the important thing to understand here is that it only will allow the type of motion that that specific joint will allow. And in the case of a hinge, it will only allow rotational motion. So you notice when I ran the analysis, the cab did not fall through. And I did not do anything to tell it that it's connected to that suspension underneath except for the hinge joint. But since the hinge joint will only allow rotational motion, then that means that there can't be any translational motion, and it is in effect connecting the cab to the suspension by creating a rotational joint. So that is the simplest way of connecting those together, but allowing the behavior. So the other types of joints that we have, a cylindrical joint is going to allow rotation and translation. So think of a cylinder inside of another cylinder. Translational allows only translational motion, so no rotation whatsoever. And then ball and socket is your standard ball and socket. So imagine a ball and socket joint, and that sort of rotation in multiple directions is allowed. So you want to make sure that you define not only your joints, but you define them appropriately. And you'll see here, so if I come here and I pick that one right there, that's going to be cylindrical. But I don't want it to be cylindrical. I only want that to rotate, so I'm going to establish that as a hinge. And then I'll come down to here, and you'll see in this case, this is a new one. This establishes it as a pin. And the reason it established it as a pin is this is just a hole that runs through these parts. Whereas this one up here, there was actually a cylinder running inside there. So it defined it initially as cylindrical, but I changed it to joint. Since this is a hole, it's going to define a pin. And the type of pin that it defined is what we call a pin. But then we also have grounded pin, which is a pin that is grounded, so it will allow rotation around it, but it can't move. And then sliding pin takes these little clips off the end and allows the bodies to slide across that. Of course, I don't want that. I want this to stay put, so my regular pin is fine. And then if I come over here and pick this one, not that. There we go, pick that. We've got that as well. Let me get out of there because I don't want that thing defined there. Okay, good. So we're moving along. Let's come along further. And there we go. And come back to joints and see what else we have here. Okay, so we've got these right here. This is actually going to be our hydraulic piston, what we're going to ultimately define as an actuator. Darn it. We'll come back to that one. Sometimes it's kind of tricky to grab what you want. So we'll try it a different way here. Let's come up to here. There we go. Okay, so these two are actually, even though they're separated, they're actually part of the same joint because they're on the same cylinder, but it's defined it as a hinge. I actually want this one to be cylindrical. And then we'll come and grab this as well and define that as cylindrical, and that will allow that, that hydraulic piston, that actuator to work. Coming up to here, this one is a really long pin. This one's going to be another pin. Let me get these pins out of the way. And then it looks like we've got another hydraulic piston here. So we'll do this, and that's going to be cylindrical. And then finally, these pins down here. And we'll go through and grab each of these. And it looks like we have one more hydraulic piston. So we'll come and grab that. And that's going to be cylindrical as well. Excellent. So think that wraps it up for the joints. And now, just to make sure that my joints are behaving in the way that I want them to, I'm going to come, and I do this continuously through my setup. Every time I perform a function, I run a quick analysis on it, and we should see, and that's exactly what we want to see. You see that the cab is standing still, the windows are staying in place, and now the arm isn't just falling, it's behaving as if it were all jointed together. These cylinders are staying cylindrical, and it's now just kind of following the flow of gravity and trying to get into its most simple state, or the most gravitationally stable state. So that's exactly how I want it to behave, and we'll move on from here. Now our next function here is couplers. And unfortunately, we have to step away from the excavator model for a minute to talk about them, because there's nothing really in that model that would apply to couplers. But couplers are a way of essentially coupling two joints together. And probably the two easiest scenarios to visualize are a rack and pinion system, where you've got a rotational translating or converting into translational motion, and then a gear system when you've got different gear ratios that are causing gears to spin at different rates. Now, we can model those physically. We could actually model the gear teeth on the rack and on the pinion, or on the gears, and simulate it by using contacts. But again, if we can go simple or simpler, by all means do that. So to view what we're going to do, and I'll show you the rack and pinion example here, and then you can just kind of correlate that to doing a gear example. But I'm going to come to couplers, and it's going to ask me to select joints here. Oops, I already got one designed. Okay, so I'm going to come to couplers, and it's going to ask me to pick joints. So the first joint I'm going to pick is my rotational joint. Well, what we've got, just to kind of explain here, I've got a shaft. All this is doing is just providing something for the shaft to go through. And then down here, I have this plug, and I have defined a translational joint. So I went through and I defined a cylindrical joint here, and I defined a translational joint. You can see those right there. So this is translational. It will allow that plug to slide back and forth, and rotational will allow that shaft to rotate. And if I come here to couplers and I pick that cylindrical joint and this translational joint, you see it shows me the little icon, cylindrical to translational, shows me which ones are active, and then it asks me for the scale. So what I've got here is, for every 360 degrees of rotation, this will move 3.937 inches. So let me just accept that, and I'll come here and I'll run it. You see what I've got here is an oscillating motor. It's going to oscillate, rotate back and forth between 360 degrees. So let me run the animation. So you see every time it goes 360, that translational joint will move 3.93 inches. If I come back to my coupler and I change the scale, I can do that over here. So say for every 360 degrees, it's going to move 7 inches. And now I run it, I'll get more motion out of there. Or if I change my coupler to every 180 degrees, it moves 7 inches, and then run it, we get even more motion out of it. So essentially, all you're doing is you're saying the behavior of one joint is going to be coupled to the behavior of another joint through this scaling factor, through this ratio. So you can imagine, if I had gears, I could set the rotation of one gear joint to be 360 degrees, and the rotation for the other gear joint to be 720 degrees, and effectively what that would be a 2 times gear ratio. So for every one revolution of one joint or gear, I get 2 revolutions of the other, and it allows me to create a gearing system without the geometric and analytic complexity of contacts. So that's how we create couplers. So next we move on to motors and actuators, how we're going to add motion to our model. Motors, of course, if we want that motion to be circular, and actuators if they want that motion to be linear. So starting off with motors, I select motors and it asks for a hole, a surface, or a pin. And what I can do is I can create a motor that goes between 2 parts. Typically one of them is ground, or the other option that I have, and I'm going to turn off the suspension here because I want to apply a motor to the cab to turn it. I can apply a motor just directly to a feature, and if I double click on that, it will apply that motor on that feature, and it's going to be a grounded motor so that it will stay put and it will cause whatever feature I put on there to turn. So in this case, the cab. And in the case of the motors, we have 4 different types of motors we can create, and the type of motor is defined by what its driving force is or what its driving aspect is. In this case, we have angle, speed, acceleration, and torque. So what do we want to be the driving factor of the motor? And it will achieve that no matter what any of the others is required. So to explain, if I set an angle motor, and I say I want that motor to turn 45 degrees, it will turn 45 degrees no matter how much torque it takes. In fact, the only thing that would stop it from turning 45 degrees would be some sort of physical lock condition. And then the solver is going to report it's going to fail, and it's going to say too much deformation in a joint or something along those lines. But it will do that. Another example would be a torque motor. So if I say a motor has a specific amount of torque, it will go up to that torque no matter what it takes to do that, and then it will stop at that torque. So it's in essence, I can use this to prove out whether a specific motor will handle a situation. So if I have a motor with a specific torque and I want to test to make sure it'll work, I can put it in there with that torque and it will tell me whether it'll work or not. Now, in the case of this motor, what I'm going to do is I'm going to establish it as a angular motor, and I'll have it rotate 60 degrees. And let me just take a quick look underneath here. And that's the way I want to rotate it. You'll see this arrow indicates the rotation direction, and I can change that for whatever I want. Next, I have to define the behavior of this motor and how it's going to do what I'm asking it to do. So it is going to rotate 60 degrees. And do I want that to be done in a step function where it will ramp up and then kind of ramp down and over whatever time I specify, and I'll show you the time in just a second, or a step-to-all step where it will ramp up, it'll go to its specified angle, it'll pause there, dwell there, and then it will come back. I can do a single wave, an oscillation, a swept sine, impulse, ramp, or a solver expression. So I can use an expression to do that, or I can do table, and we'll get back to tables in just a few minutes here. So now that I've got the motor defined, and I've defined it as a 60-degree motor, let me come over here to the property browser, and you'll see the profile. And this here too, if you don't want to go off the little icons here, I can see all the different functions that will drive this, and step is what I'm going to leave it at. It has a start time, so start time corresponds to the start time of the motion analysis. So 0 is the beginning of the motion analysis. The nice thing about the start time is it allows you to stage things. So if I have things that I want to go in a certain order, I can have one go for, say, a second, and then have the next thing start at a second and go for a second. So I can stage things. And then the duration, in this case, I'll say 1 second. That's all I'm running these for right now. And now if I come back here and I take a look at this, and I come to this little icon, looks like a little table. I click that, and it's actually going to show me the function here. So I can see a graphical representation of the function. You see it's going to slowly ramp up, and then we begin a steady rotation that'll slowly ramp down. So I get a nice smooth rotation out of that. And as I change that to different features here, so this is now actually going to pause. It's not going to come back because I've only defined it up to a second. So it's going to start at 0. It's going to step on for half a second. It wants to pause for 1 second and then step off, but my analysis isn't defined for that long, so I'd need to actually define it longer. And now we can see the entire function here, and I could go through each of those. I can also come here and go to a table, and now I can put in just direct values. It's going to be x versus y, so time versus angle. I can put those in myself, or I can import them from a CSV file. But I'm perfectly fine with just my simple step function there for 1 second. So you see we have the ability to drive the motor however we want, and that table would correspond to whatever type of motor it is. So in this case, it's time versus angle. I could do time versus torque, time versus speed, whatever. So I'm good there. And now if I quickly run my analysis, or run my, yep, there we go. And you can see over the course of a second, it will turn 60 degrees. And I'll see that behavior. The rest of this is just still falling as a result of gravity. But this is exactly how I wanted it to work. So that's my motor. And then I also like to turn off the motor just so it's not being shown. And I'll turn my suspension back on. Now we move into how we control linear motion, and that's going to be done with an actuator. So my actuator here, the interface looks very similar, and I have a couple of different ways, 2 different ways I can define an actuator. I can either define it between features or between aspects of my model. I won't say parts because it's not between specific parts, but features like a face or a point or a line, or connected parts. So we'll start with features. If I select a feature, so we'll say the face of that right there, it says now click a position to add for the actuator base. So I'll select that, and you see it creates I picked there. That's fine right there. So it creates an actuator that and it calculates a distance, but I can have a distance, a velocity, an acceleration, or a force. And then just like with the motor, I have different functions that I can select. So you see the similarity, they're very similar between the motor and the actuator. It's just whether I want linear motion or whether I want rotational motion. So I can create these physical or these representations of actuators when I don't have a geometric representation of them. But in this case, I do have a geometric representation of them, and that's these hydraulic cylinders. So if I come back to actuators, and instead of features, I say connected parts, now it identifies what can be an actuator. It's looking for cylinders that are inside of other cylinders with a cylindrical joint defined there. And actually, I can just create all. And it's not going to create that graphic that you saw previously. It's just going to create this little arrow here. And that's now the actuator because it's going to use the geometry itself as the graphic. And to alter it, I just simply select any of those. So if I come here and there we go. That's what I'm looking for. Double click on that. It's going to move, in this case, it's calculated 29.6457. I would specify whatever I want that to be, so we'll say 12. Oops, there we go. And of course, I need to change this one too, because they're both acting on the same thing. And so I've got a distance actuator. And it will move 12, and it's a step dwell step. So I'm going to change that again to a step, and I'll say from 0 to 1 second. And then I'll need to switch this one as well. They both need to match. If not, it's going to have some issues because they're both controlling the same thing. And if I right click now and run the motion, so now we get the behavior of the actuator, and I probably can increase that actuator a little bit. But if we review this, you'll see that initially it's going to sag down a little bit, but then it will begin to go up, and I get that arm going up. And I probably could alter the actuator a bit to better move that out. But we get that sag, and that sag is because of the same situation that we were getting with the motor, where, oops, let me get out of the function here, where it's going to smoothly step up. So right now it's beginning to push, but it's not overcoming gravity quite yet. So gravity's pulling it down while I'm in this lower portion right here, but then it will overcome gravity. So that's why we're getting that little sag at the beginning. And interestingly enough, if I come back here and I grab the actuator, you can see the distribution of the force through the entire analysis there. So I would create my actuators there, and then I've got my actuator here, and I actually now will get the behavior of the part that I'm looking for. So that's how we can create motors and actuators to drive our part or our assembly. Our next function is springs, and springs, pretty self-explanatory. It's how I can create a spring. And we can create a spring between different parts, pins, fasteners. So let me represent something here. So I'm going to come here. Let me ground this box right here. And we'll analyze it for just a quick second here. And of course, if I click run, that other box just falls. This one stays put because I've got a ground on it, but this one falls. So, but now if I come here and I activate springs, and we're going to create a, you can see that we can also do coil or torsion springs. So I'm going to do a coil spring, and I'll connect from that face to this face right here, and we get the spring. And now you'll see if I run the analysis, it just kind of jiggles there. So it begins to fall, and we get a little bit of jiggling action there. So it's very easy to create a spring. And it looks like, you know what, let me get rid of that, and let's see if I can get the exact center of this. No, you know, it's probably not, you know, whatever, that's fine. I could eliminate that wiggle by getting it the exact center, but that's fine. So once we create the spring, we've got the ability to put the spring stiffness and the damping coefficient in there, and we can change those as necessary. Additionally, we have free length and installed length. So what that's going to allow us to do, and sometimes it's easier just to work it from here. Let me get out of the spring here. So free length is what the spring is just naturally, and installed length is what it is in my actual model. So the free length right now, and I can't change the installed length because it's set between these two surfaces right there. But if instead of a 2.00041 installed or free length, if I change that to 1, you see the installed length stays the same, but now it has a preload on it, and it automatically calculated that preload based upon what the spring is right now and what it wants to be. So now if I run it, you see the very first thing that happens is it begins to compress the spring because it wants to compress, or it wants to go back to its normal length, its free length. So it's going to essentially put a preload on that spring. I can also, and there's a damper force on there as well, but I can also come here and instead of changing the free length, if I set the preload as 0, then the free length is exactly the same as installed length. But if I now say, okay, I want 100 pounds force on that, so the free length is 19.1, the installed length is 2. If I run it now, it's going to shoot that down. So I can control it either by changing the free length of it or by changing the installed length. And coil springs are a similar manner. Torsion springs are a similar manner. It's just then I'm going to get, as opposed to linear action, I'm going to get rotational action. So springs are very useful. And also, I might add here, if I come back and double click on it, the default is to create a spring damper system, but I can create just a spring, just a damper, and also and this does not affect the behavior of the spring, but I can also change the appearance as well. So I've got an overall diameter, so I can say 0.5. It will change the diameter of the spring, and I can also affect that by doing that there. I can say the number of coils, and then I can also change the wire diameter here. So I can change that, the look of the spring as well. So that's pretty much it. The next feature we want to talk about in motion is the contacts. And the contacts are the way of specifying how some object is going to interact with some other object. And we need to define that. So I've got this set up right here. You'll see I've got this part's grounded, that part's grounded. I already put a joint pin in there and that part right there. So if I come here and I run this for a second, you'll see that my arm will come down here and it will swing. And the ball is just going to pass through the table. And even if the ball didn't pass through the table, the arm would pass through the ball, because by default there's no interaction between them. So to get that interaction that I want, I actually have to define a contact. So I'm going to come here to my contacts, and what it's going to do is it's going to ask for part 1 and a part 2, and I can have multiple of them. So if I had multiple balls on this table, I could select them all as part 1 and then the table for part 2. But since I just have one, I pick that and come and select part 2, specify the table, click create the contacts, and then I can indicate whether I want friction to be enabled or not. And if I select friction, then I can say it's static and dynamic. What's the static coefficient? What's the dynamic coefficient? And then what's the stiction transition and the friction transition velocity. But I'll just leave the friction off of those. That's not necessary. And so I've got that. Now, right click to get out of there, come back to contacts. And this next contact, I'm going to say I want a contact between this and a contact between the ball, and create that contact. Again, I won't use friction. And what's going to happen now is the ball will not pass through the table due to gravity, because that contact is going to prevent it. And then this will swing down, and when it hits the ball, it'll knock the ball away. So we can create some relatively complex interactions through the use of contacts. And we can play around with those contacts a bit more advanced, but we can change the stiffness of it, the damping, and the penetration depth. So without getting too deep into the weeds, the solids will begin to pass through each other. Once they reach the penetration depth, the solver puts a spring stiffness to bring it back to the other side. And then with the damping is what will damp that as well. So we can create some fairly complex interactions between solids, between multiple solids, using the contacts. And this is what we would do if we could not handle it through the creation of a joint. A joint is always the first choice if possible, but remember that a joint is a very simplified motion, whereas a contact is going to be a more complex motion. The other thing about contacts is they do require more analysis time, so they are a little bit more expensive from an analytical standpoint. But we can also do things like when we have contacts now, I can come to Force Explorer, and now you'll see when I turn on my motion. Let's get rid of that right there. Okay, come back to here. Oh, stop that. Pop out, and then we'll turn that off. Perfect. And now as I come along here, you see it's showing me the force between the ball and the table, and then I will get, an instantaneous force somewhere in there. Between the, there, we saw it kind of flash there. And you'll see it again. Let me see if I can pause it right when it happens. There it is right there. So I'm getting an 8.94 pound force as a result of this little arm hitting the ball there, and I've got 3 pounds force up as a result of the ball sitting on the table. So we can explore the contact forces as well once we've established those. So that's pretty much it for contacts. One more thing to talk about, and we'll wrap this up. So the last two things we're going to talk about, and we'll stick with this model here for them, are the last two icons here, which are the initial conditions and gravity, and we'll combine them because they're relatively short topics. So initial conditions just define an initial condition for one or multiple of our bodies, and we have initial condition for translation and for rotation. So translation, if I select, say, this ball here and create an initial condition, and I'll say it's initially moving at 2 inches per second in the X direction, negative. And now I run the analysis. You'll see it will start out by rolling, and then this will come and meet it. And I can speed that up or slow that down. I could do a rotational initial condition on this right here, and we'll say 200 RPM. Yeah, that'll work, and that it's rotating, yep, in the axis that I want. So right click that and do this, and you'll see, so initially now when I run it, it initially starts going up because it's it has that initial rotational velocity, but then gravity kind of takes over, and we go from there. And I could mess with the ball and increase it and possibly even make it so the arm doesn't even hit it. Now this is being driven entirely by gravity. So we talked a little bit about gravity earlier, but there's gravity right there. I can affect the direction that I want gravity to go in. If I were to say change gravity to that direction, and then right click from this and run this, you see the ball would now completely fall off the table, and the only reason the arm is spinning is because of that initial condition. It wouldn't want to. So I can mess with gravity in whatever way that I want, point it in any direction, and I can also affect the acceleration due to gravity, or I could just turn gravity off if I wanted to do that. I could say set it for 0, and in that case, if I set this for 0 and now run it, I have my initial condition of the ball because it was set to go forward. The arm will not fall down at all. It will just go based on the initial condition of its 200 RPM going in the opposite direction. So I can create just about any scenario I want to based upon the initial conditions and gravity as well. So the last thing I want to cover is the Analyze Motion button. We actually still have the Analyze part, Optimize part, tracers, but we'll save those for another video. The Analyze Motion, right now we've just used it to run the motion analysis, but we haven't talked a lot about this this screen right here. So what I can do is I can specify the amount of time that I want the motion analysis to run. I've been leaving them at a second just to get quick views as to the behavior of my model as I go through and set things up with the excavator or with this model here. But I can set whatever duration I want, and then output rate. So what will happen is the output rate is going to output information and essentially a state of the analysis at that frequency. So at 50 hertz for a 1 second analysis, I'm going to have 50 pieces of information, 50 things that show up in that plot, 50 points. The more you specify, the smoother your animation is going to be, the more information you're going to have in your plots, the slightly more stable your analysis is going to be, but the longer it will take. Then we have animate while solving and when finished. Now for these short analyses, I've been leaving it while solving so we can see it as it's going along. But I find that when I actually run motion analyses on things I'm actually working on, it's best to set it to animate when finished. It does speed up the solution a bit because it's not having to animate it at the same time as it's solving it. And then whether I want to include gravity or not, and whether I want to analyze with the contacts or not. And then there's some other features in here. Typically leaving these alone is going to work fine. We won't get into all of these different integrator orders and step size and all that sort of stuff right now. Maybe we'll make a more advanced model, or in the interim, just check in the help documentation that will specify what all of these different features are in here. So when you put it all together, motors, actuators, contacts, joints, you can see the behavior of your model, determine the kinematic motion, make sure everything works out okay, and as I mentioned before, even send it into analysis and optimization. So that pretty much wraps it up for motion. Look for future videos covering the analysis and optimization coupled with motion, and take a look at Altair Inspire and see what the motion can do for you.